in a landscape made up of literally billions of dimensions, we aren't just talking about abstract math anymore. It's a literal modern technological miracle. The fact that simple gradient-based methods can reliably find parameters that actually work in the real world, it's just astounding. To understand how that miracle actually happens, though, we need the right tools.
So here's our roadmap for today. We're taking exactly 5 essential tools out of the box. Number 1, probability. 2, linear algebra. 3, information theory. 4, optimization. And 5, sampling. All right, let's jump right in. Tool 1, probability, the native language of AI. Now, a trained language model doesn't actually think in English or Spanish, right? It thinks entirely in chances and likelihoods. And the master equation behind all of that is the chain rule of probability. Honestly, this equation deserves a moment of absolute reverence. It is the master equation of modern generative AI. It essentially states that any joint distribution over a sequence, no matter how massively high-dimensional or complex, can be exactly decomposed into a product of one-step conditionals, no approximations. It's this exact mathematical identity that makes generating a realistic sentence possible in the first place. Let's actually see it in action with a really simple 3-word sentence. The cat sat. The model starts by calculating the probability of the word the. Let's say that's 0.42. Then it figures out the probability of cat, given that the just came before it, maybe that's 0.18. Finally, it looks at the probability of sat, given the cat, which comes in at 0.55. You just multiply those tiny probabilities together, and boom, you get the probability of the entire sequence. Basically, an autoregressive language model is simply a neural network that's been trained to represent these exact little factors. Okay, moving on to tool 2, linear algebra, how the AI computes. So if probability is what the model represents, linear algebra is how it mechanically crunches those numbers. The huge takeaway here is that AI processes text using vectors, which at the end of the day are just lists of numbers. You can think of vectors as the universal currency of meaning. When you feed a word into a model, it becomes an embedding, a vector floating in a massive, high-dimensional space. And the geometry of that space perfectly captures human semantic relationships. Take the famous vector arithmetic example, king minus man plus woman. It's wild, but that lands you precisely near the vector for the word queen. It's literally mapping out human meaning using pure geometry. But an AI doesn't just do this one single word at a time. It uses a tensor hierarchy. Now, a tensor is just a fancy word for an array of numbers. Rank 0 is your basic scalar, just a single number. Rank 1 is our vector for meaning. Rank 2 is a matrix, which handles transformations and neural layers. But deep learning, it lives way up at rank 3 and above. Why? Well, it all comes down to economics. Scaling up to higher ranked tensors lets GPUs batch massive amounts of sequences together all at once. The whole art of efficient training is essentially just keeping these tensors huge and uniform so the hardware can absolutely sprint. Up next is tool 3, information theory, measuring surprise. We know how the model speaks and we know how it computes, but how does it actually know if its predictions are right? To measure this, we have to look at the science of quantifying surprise, contrasting 2 vital concepts. First, entropy. This is the intrinsic uncertainty in the data itself. Think of it as the absolute floor of predictability. You can never predict text better than the inherent randomness of natural language allows. Cross-entropy, on the flip side, is the average surprise a model experiences when it believes its own predictions, but reality decides to do something completely different. Believe it or not, the entire trillion-dollar enterprise of pre-training large language models is quite literally just the act as minimizing this cross-entropy. Let's look at the actual math behind that surprise, which is measured in a unit called nats. Say the true next word is cat, and the model gave it an 18% probability. That loss is 1.71 nats. If it was super confident and gave it a 90% probability, the loss is tiny, just 0.105 nats. But watch what happens if the model confidently gave cat only a 1% chance. The loss absolutely explodes to 4.6 nats. This brilliantly shows the asymmetry of logarithms. Being confidently wrong is punished far more severely than just having diffuse spread out uncertainty. Which brings us to a term you're going to see a lot if you read AI literature, KL divergence. Let's strip away the intimidating jargon for a second. KL divergence is really just the measurable extra surprise that represents a model's error. Since the underlying entropy of human language is a fixed constant completely beyond the model's control, minimizing cross-entropy is mathematically identical to shrinking this KL divergence. You're basically just forcing the model's distribution to perfectly match reality's distribution.
Now, in the real world, you'll often hear engineers refer to perplexity. If a model has a typical training loss of, say, 2.1, that translates mathematically to a perplexity of 8.2. But what does that actually mean for us? It means the model is, on average, as uncertain about the next word as if it were choosing blindly among 8 equally likely options. It's just a fantastic standard metric to gauge how confused the model actually is at any given moment.
Moving right along to Tool 4, Optimization, the engine of improvement. So we know we need to minimize that loss and reduce that perplexity. But how do we actually do that across billions of parameters in a messy, totally non-convex landscape? We rely on iterative optimization, and man, has this field evolved rapidly. We started way back with full batch descent, which was exact but horribly slow. Then came stochastic gradient descent, calculating quick mini batches. Then we added momentum to help smooth out all the noise. That eventually evolved into Adam, giving each parameter its own custom learning rate. And finally, we arrived at AdamW, which cleverly decouples weight decay. Today, AdamW is basically the de facto standard recipe for training massive transformers.
But here's the catch. AdamW alone just isn't enough when you're burning through millions of dollars on compute. You absolutely need massive scale stabilizers. You've got linear warm-up, which ramps the learning rate slowly so you don't instantly break the model early on. Cosine decay gently tapers it off. Gradient clipping is crucial because it stops sudden massive errors from ruining the whole run. And mixed precision arithmetic saves precious memory by using 16-bit math wherever possible. These are the unsung heroes that prevent massive, wildly expensive training runs from literally exploding into errors.
And finally, Tool 5, Sampling, Generation and Creation.
Okay, so we've got a fully trained, highly optimized model. How do we actually get it to talk? We use something called ancestral sampling. It runs that chain rule of probability we saw way earlier forward. It takes those raw probabilities and turns them into the streaming text you actually read on your screen. And to control this generation, we use a literal creativity versus reliability dial known as temperature. At a baseline temperature of 1.0, the leading word might have a 63% chance of being picked. If you drop that temperature down to 0.5, the math dynamically alters, making that leading word a massive 84% favorite, which gives you very safe but highly repetitive text. But if you crank the temperature all the way up to 2.0, the probabilities flatten right out. The leading word drops to a 48% chance, giving you highly diverse, sometimes risky, but incredibly creative outputs.
So let's bring the whole shebang together. Here is our complete, demystified mathematical toolkit. Probability is the native language the model speaks. Linear algebra is the roaring engine that computes the data. Information theory acts as the ruler, measuring the surprise and error. Optimization is the iterative engine that actually learns to reduce that error. And sampling? That's the creative spark that generates the final output. They all flawlessly lock into place as one beautifully unified generative system. Before we wrap up, I want to leave you with one final provocative thought. Everything we've covered today beautifully explains how AI generates text, step by step. But what about images? How can taking iterated, noisy gradient steps on a mathematical landscape turn pure, static noise into a hyper-realistic photograph? Well, that specific question sits right at the heart of Langevin dynamics, and it's the exact magic that powers modern diffusion models. But hey, that is a whole new toolkit for us to open next time. Keep learning, stay focused, and I'll see you in the next explainer.